The loads on a structure are fundamental to its configuration and design. Without loads, we have nothing with which we can compare member strength. We see the impact of loads and load paths on how classic structures like the Van Buren Bridge were designed. In this video, you will learn about loads on bridges, how to combine them, and how they move through a bridge. We will focus on fundamental types of loading.
The most common loads on a bridge are dead load and live load. And dead load is just the bridge has to carry its own weight. And that's the biggest job a bridge is going to have, is carry its own weight. And then live load is the vehicles that are on it. And typically we consider trucks that are on the bridge, although pedestrian loading can be significant. If there's a bridge that's closed and there's a major event where thousands of people are on it, it can see more loading during those times than it would with trucks.
Bridge loads include permanent, live, water, wind, temperature, ice, earthquake, friction, vessel collision, and blast. Permanent loads are comprised of dead, including self-weight, utilities, and wearing surfaces. They also include earth forces, specifically pressure, surcharge, and downdrag. Live loads consist of traffic and pedestrians. A great deal of experience and research goes into developing the load requirements in design codes. AASHTO defines two primary types of dead loads: components and wearing surfaces. Components include all the elements of the structure like steel, concrete, deck, and connections. Wearing surfaces consist of concrete or asphalt overlays, which are replaced or added to over time. These have different load factors that account for their relative variability. Unit weight tables, like this one, can be a great help in determining dead loads on structures.
The design vehicular live load has changed over the years. We have what's called the highway truck. Then you put a trailer on it, it's called a highway semi-truck. So it started out being a H15, which is 15 tons. Then it went to 20 tons in 1944. Then it went to 25 tons, and they just kept getting bigger. And so in 1993, Bridge Design Committee came up with what's called the Highway Loading 93. And it's a combination of an HS20 truck, which is 40,000 pounds on the part of it. And then it's got a concentrated load, and it's also got a distributed load. So that was made to describe the loads bridges are facing, but it's a load that cannot be reverse engineered. It's not a truck. So vehicular live load is used in superstructure design. What we're going to do is we're going to position those loads in the most critical spot for each member we're designing, and we'll move those loads around on the bridge. We'll load multiple lanes and just get the most severe load combination for that particular piece, and that's what it's designed to.
Live loads on a bridge consist of a 640 pound per foot line load spread over a 10-foot wide strip plus the design truck. These loads are moved around to create the greatest impact. Each member is then designed for the worst-case effect from the varying load positions. As water and ice flow past bridge elements, such as a pier, they induce pressure onto them. The AASHTO design specifications provides guidance on these pressures. Engineers apply them to the structure and evaluate their effect. Wind is one of the major environmental influences on bridges. As wind passes across a bridge, it creates pressure on its members. This causes localized and global effects on the bridge. Wind pressure is a function of wind speed squared. Hence, a small increase in wind speed has a substantial impact on pressure. Speed squared is modified by three factors: exposure and elevation coefficient, K sub z, gust factor, G, and drag coefficient, C sub d. These factors are found in the AASHTO code. Wind speed is found from maps provided in the AASHTO code, which provides the 3-second gust wind speed. A driving variable in wind pressure is ground surface roughness, which inputs to K sub z. There are three roughness categories, B, C, and D. Category B is defined as urban, suburban, and wooded areas with obstructions the size of single-family dwellings. Category C has scattered obstructions and includes flat, open country and grasslands. Category D is categorized by open water and mud or salt flats. As we move from category B to D, there are fewer obstructions and thus higher wind speeds. The pressure exposure and elevation coefficient K sub Z considers surface roughness and elevation in the structure. As we go from exposure category B to D at a height of 33 feet, the coefficient increases 62%. Similarly, as we go from a height in the structure of 33 feet to 300 feet, this coefficient increases substantially. Gust effect factors are typically 1.0, except for sound barriers. Drag coefficients vary depending on the surface shape. These vary from 1 to 2.0 for the windward surface. Once we find each of these variables, we can proceed to calculate wind pressure given by this equation. Following these procedures, we can apply the wind pressure to the Van Buren truss by multiplying the unit pressure by the projected width of the member, which gives us a line load for each member. This allows us to check local bending and the forces in the two horizontal trusses and portal frames.
Wind loading and seismic loading, they're going to follow the same load paths that the other loads would have. The seismic loading, that's going to come though from the bottom of the bridge. It's going to be transferred from the foundation up through the columns to the bearings into the superstructure. It's going to be more complex. It could be a combination of vertical loads, horizontal loads. It could be a series of aftershocks. The bridge is going to be vibrating. So seismic loads can vary greatly between seismic events, and we learn from every major seismic event and change our codes because of it. So there's a lot to be learned in the field of seismic. When it comes to earthquakes, of course, California, they've had some major earthquakes down there, and they've had to replace many bridges. And then I think even some bridges they replaced, they get hit on a next earthquake or another earthquake. So we're learning all the time when it comes to earthquake loading.
The magnitude of potential seismic activity varies significantly across the United States. The West Coast, portions of the Intermountain region, and Mississippi River near Memphis and South Carolina coast have the greatest seismic risk. Maps like this one provide seismic data such as the peak ground, short period, and 1-second accelerations. Engineers use these to predict the seismic effects on structures. The acceleration a bridge experiences is the function of its periods of vibration. If we plot period along the x-axis and acceleration response on the vertical, we see that for short periods, seismic accelerations are very high and drop as the period increases. Stiff bridges, of which there are many in the world, fall in the highest acceleration portion of the curve. There are two fundamental seismic design methods for bridges: force and displacement. They both use seismic force, which we will discuss here. In the force-based method, we apply calculated lateral forces on the bridge and evaluate their effect. We allow some elements to yield and keep other elements elastic. This design force is applied to the structure as a distributed horizontal line load. In its simplest form, this load can be used to evaluate the resulting member forces in the super and substructures. The seismic force P sub E is a function of the seismic response coefficient, weight of the bridge, and length. C sub SM is given by this equation. For periods of vibration between T sub 0 and T sub S, it is equal to S sub ds, which is a function of the soil site factor F sub A, and short period mapped acceleration S sub S. Two more key seismic analytical methods are available for structures, namely response spectrum analyses and time history analyses. In a response spectrum analysis, the engineer determines the dominant periods of vibration of a structure. They find the corresponding accelerations and apply them to the mass of the structure in proportion to how much this mode contributes to the overall seismic behavior. This results in a reduced seismic force on the structure. In a time history analysis, the engineer creates a three-dimensional model of the bridge and runs actual earthquake acceleration time histories through the model to determine the structure's response. Multiple earthquake records are used to capture a wide range of possible outcomes. This is the most robust seismic analysis method.
So load combinations could be your, well, you've got, of course, the live load, you've got wind loading, but seismic loading, again, that's another load, but seismic is something that happens very rarely, so we don't combine catastrophic loads together. The odds of both of those happening at the same time are slim. We don't want to be so conservative in our design that we can only afford to build a few bridges.
Load combinations rationally predict what loads will act together. Engineers then apply load factors to account for uncertainties in the loads, and to emphasize certain types of load cases. Later, in member design, engineers multiply resistance factors by member strength to account for material uncertainties. AASHTO defines several groups of load combinations: strength, which includes dead, live, and wind loads; extreme events considers earthquake, blast, ice, vehicle and vessel collision loads; service, in-service effects such as deflection and crack control; fatigue focuses on the cyclic effect of live loads. Looking at load combinations in table form, we begin to see which loads will likely act together and their corresponding load factors. Each combination tends to focus on a given type of load with lesser magnitudes of other loads. For example, in Strength 1, live load is emphasized and has no wind load. In Strength 3, wind load is emphasized with no live load. This checks the maximum wind the bridge might see in its design life. Much goes into the development of load combinations and their load factors. Looking at permanent load factors, we begin to see the amount of effort that goes into utilizing load combinations. We also see the relative weighting between different types of permanent loads. For instance, the load factor for dead components in most combinations is 1.25, while that for wearing surfaces is 1.5. This is because more variability occurs in the weight of wearing surfaces. Also, note this table contains a column for safety factors less than 1. These are used when the effect of dead load helps the structure, as is the case in overturning.
Gravity load paths, that's going to, if you think of a bridge as like a set of blocks, and the top block is going to transfer loads to the next block, down to the next block. So we'll start with the deck of the bridge, and that's where the cars and trucks drive on. That's going to be then transferred into your primary superstructure members, probably steel girders or a truss. Going to go down into the bearings and then into the substructure and foundations. And foundations can vary in different ways with spread footings or piles. So it just goes straight down from the top of the bridge down to the bottom of the foundation.
Well, lateral load paths in a truss they're there largely to resist wind forces in the day that they designed these bridges. Seismic was a linear design at that time, force-based, and the lateral load system is X-bracings that occur in the horizontal planes. That brings the load down to the bearings in the lateral sense, keeps the bridge stable in the sideways sense. They differ quite dramatically. I could see that as seismic became more of an issue. I could see that in some ways wind loading becomes the enemy of seismic loading, because wind load, you're trying to get these high wind loads that occur, that drag on the strut, you're trying to get them down to the bearing. And by stiffening the vertical members and bracing the vertical members, you could bring that load down to the bearings. In seismic analysis, it's not force-based, it's displacement-based. And the loads are applied differently, and that same stiffness becomes an enemy of seismic design, because they want flexibility to allow the ductility of the steel, the yielding of the steel, to absorb the energy. Seismic is much more complicated.
Let's look at how vertical loads work their way through the Van Buren truss. Lane loads flow horizontally through the deck, timber beams, and cross steel beams to each panel point. The truck loads move to panel points as well, based on their position on the truss. These loads move up the truss diagonal web members, creating tension forces, and back down the vertical members, creating compression forces. They eventually deliver a vertical resultant to the abutment. Because the forces are eccentric to the abutments, they create a bending moment, which is resisted by tension in the bottom chords and compression in the top. In Module 4, we will use statics to understand this further. Turning our attention to lateral loads, let's consider how wind loads in the Van Buren Bridge work their way to the bearings. As wind flows across the bridge, it applies a higher pressure on the windward side of the bridge and a lower pressure on the leeward side. These loads work their way to the panel points by bending the members they act on. They then enter the horizontal truss members in the top and bottom chords. On the bottom level, the wind forces work their way directly into the bridge abutments, where the bridge concrete pier pushes back against the wind. Remember Newton's third law? On the upper level, the wind forces make their way to the portal frame on each end of the truss. The portal frame resists lateral forces through bending in the posts, which are the primary truss end members, and tension and compression in the connecting truss. This allows vehicles to pass and loads to flow around the opening. This module has been focused on demand, primarily loads. The other side of the equation is capacity. As long as the structure's capacity is greater than its demands, it will perform as intended. In structural steel design, this is called required strength and design strength. How much of the demand and capacity curve overlaps is a function of our society's acceptance of failure, which is built into safety factors. In equation form, these curves are represented as demand on the left and capacity on the right. Demand is found by multiplying the force effect Q sub I by ductility, redundancy, operation, and load factors. Capacity is found utilizing principles of mechanics of materials multiplied by a resistance factor. This equation forms the basis of all structural design. In this video, we have introduced the fundamental loads which occur in bridges and focused on permanent, live, wind, and earthquake loading. The AASHTO LRFD bridge design specifications greatly expands on these and other loads and provides extensive guidance on how to apply them. With this information, you now have the basics of bridge loading that will input into every aspect of your structural designs. In the next modules, we will use these to analyze trusses and beams and input them into finite element software and seismic design.